So we're still on chapter 2, thermochemistry, and now we're moving on to heat of combustion. So the heat of combustion of a substance is the heat change when 1 mole of the substance is completely burned in excess oxygen. So a combustion reaction is just when something is burned, which is the same as it undergoing a reaction with oxygen. So I have 2 things underlined in that definition. The first one is that the substance has to be completely burned in excess oxygen. The reason for that, as you can see with these 2 examples, the first one is carbon reacting with oxygen to make carbon dioxide. That's showing me that all of the carbon is reacting with all of the oxygen to form carbon dioxide, and so the heat of combustion for that one is minus 394. If we were not to have excess oxygen, if we were only to have half the amount of oxygen, you can see that has a big impact on the heat of combustion value here. It's less than 1/3 of what it was when the carbon dioxide or the carbon was completely burned in the oxygen. So that's a very important part of this definition. That will be half the marks for this definition. The other thing underlined is the fact that it's 1 mole. So if we look here again, and we briefly mentioned this in the heat of reaction in the last video, here I've got 2 moles of C4H10, and the heat of combustion for that is minus 5,754. So that's actually for 2 moles of the butane there. So in order for to get the heat of combustion, it has to just be 1 mole of the substance being burned, and then we'll get the heat of combustion for 1 mole. So again, you could do it this way, and if you were given a reaction like this, you would be expected to give this definition probably as part A of the question, and part B would be expecting you to know that you must divide this number by 2 to get the heat of combustion value for butane. Heat of combustion is done using, or is measured, I should say, using a bomb calorimeter. So a calorimeter is a container that's used to determine heat changes in a reaction. So we'll go through the steps here, and I do have a picture of this on the next slide so we can work back and forth. So a known mass of the sample is placed in the crucible inside the bomb. So this is the crucible, the little bowl that's inside in this part, this bigger part here, that's called the bomb. So the crucible holds a fixed mass of the sample, or a known mass of the sample, and then that's placed inside this piece of apparatus, which is the bomb. The bomb is filled with oxygen under pressure. So there's an oxygen inlet here, and that is going to be filled with oxygen, the inside of this bomb, so that we get our excess oxygen in there. The bomb is placed in a known quantity of water in the calorimeter. So this big tub here, that's the calorimeter, and you can see the blue color there is it filled with water on the inside. The sample is ignited electrically using an ignition coil of wire. So in here you've got your wires, and you're going to ignite the sample, so set it on fire, start the burning of it, start the combustion, using these electrical leads. The rise in temperature of the water is measured. So what that's going to create is that's going to create heat in here. So this combustion reaction between the sample and the oxygen that's filling up the bomb, that's going to create heat, and what we get is, or it could end up taking in heat as well, sorry. Whatever happens, it's going to change the temperature of the water. If this produces heat, it's going to it's going to raise the temperature of the water. And using this equation then, the mass of the sample that we measured out, specific heat capacity, we'll get onto a little bit more later on, that's just a value that will be given to you in the question, and the change in temperature, that allows us to multiply those together to give the heat given out. And because we've got a fixed mass of the sample, we know how many moles of the sample we began with, and we can then use that information to calculate how much heat would be produced for 1 mole. Couple of things to note on this. The apparatus is well insulated to prevent heat loss. So the calorimeter is an extremely well insulated instrument so that any heat produced by the sample combusting is going to be retained by the water. It's not going to be released out into the air. And the amount of heat used to start the burning can be calculated and removed. So the amount of heat that's created to ignite the sample, that can be removed for calculations. Bomb calorimeters are also used to compare fuel efficiency. So you can put fuel in here as your sample, and what it does is it allows us to compare different fuels to each other, see which ones, for the amount of them that there is, see which ones produce the most heat, because generally that's what we want from a fuel. So it's calculated by dividing the heat of combustion by relative molecular mass. So we've got a fixed mass in there. If we divide that by relative molecular mass, that should sound familiar to you, we'll get the heat given out by 1 gram. And for fuels, what we want to do is find the heat given out by a kilogram. And so we find it in 1 gram, then we multiply by 1,000 to get it in kilograms. And what that's called is the kilogram calorific value of the fuel. And that is the heat energy produced when 1 kilogram of the fuel is completely burned in oxygen. And that just gives us values to compare the efficiency of different fuels. We can see some of them here. I've just taken this out of the book. So this is the heat of combustion, kilojoules produced per mole, and here this is it, kilojoules produced per kilogram that's been burned, and that's the kilogram calorific value. And you can see there, this provides a good way of comparing the fuels. One thing that they often ask about is methane, and methane is an excellent fuel because it has, if you look relative to all of these other substances, ignore the last one for a second, it has a very high kilogram calorific value. It burns with a very clean flame, and it's easily distributed to homes and industry through pipes. There's not many issues in being able to distribute it. Just to note here, since earlier in this chapter we were talking about hydrogen as a fuel, and we spoke then about hydrogen being an excellent fuel, and you can see here that it is. It's nearly triple as efficient as methane, which is one of our better fuels that we have at the moment. You should recall the reasons why hydrogen isn't used as a fuel at the moment. And the reason for that is that it forms an explosive mixture with air. And so this leads to a lot of problems regarding storing and transporting the gas. So it's not very safe for use at the moment. Other substances that have variable composition, things like petrol that you'll remember from our fuels, coal and peat, so they have variable composition, they're not pure. Their kilogram calorific values are measured using the bomb calorimeter as well. However, because they're not pure, we haven't got them listed here because we don't actually have specific values for them, because their composition can vary depending on what sample you get. We only have approximate values for those. So you do need to know why we can't have a specific value for petrol, coal or peat, for substances with variable composition.